We're starting Unit 2 now, and our first topic of discussion is going to be over aortic regurgitation, or aortic insufficiency, however you want to say it. So we'll be discussing the pathophys of such, types of regurgitation, AI types, either acute and chronic would be the two types we're going to discuss, the hemodynamic consequence of each, and how to quantify aortic regurgitation according to the guidelines. So normally, let's just go over how the pressure changes in the heart move blood through the different valves in the heart. So normally the aortic valve is only open when the pressure in the ventricle is higher than the pressure in the aorta. And we're talking about the left ventricle, of course, because that feeds the left ventricle of the aorta, right? So blood is ejected into the aorta. That's referred to as the stroke volume, a certain amount of blood, somewhere between 70 and 100 mLs per beat normally. And greater than 50% of that blood is ejected, right? Because we get our EFs if greater than 55% is normal. So after systole, after ejection, the pressure in the LV decreases, and as it relaxes, it begins to fill with blood from the LA. And relaxation causes a fall in pressure. And that's why the mitral valve opens and starts filling blood through the LA. When the pressure falls below aortic pressure, the aortic valve closes, preventing blood in the aorta from going back into the LV. So that's how it's supposed to happen. So the LV fills when LV pressure falls below LA pressure. Well, if the aortic valve doesn't completely close, blood from the aorta is going to leak in. Now remember, some of that blood was already ejected, and that's leaking back into the left ventricle. The percent of blood that leaks back due to the insufficiency of the aortic valve is known as the regurgitant fraction. This regurgitation causes a decrease in diastolic blood pressure in the aorta because it should be up there, now it's down into the left ventricle, and therefore an increase in what's called the pulse pressure. So the pulse pressure is essentially the difference between the systolic and diastolic blood pressure. And it represents the force that the heart generates each time it contracts. So an example of that would be if the blood pressure is 120/80, then the pulse pressure is 40. Since some of the blood ejected leaks back into the left ventricle during diastole, during the filling phase, the forward flow is decreased, is affected by that. So there's a decreased effective flow going back out. Just a reminder, the Frank-Starling law of the heart states that the greater the volume of blood entering the heart during diastole, the greater the volume of blood ejected during systolic contraction, stroke volume and vice versa. How does that apply to AI? I'll give that some thought. So our main goal as echocardiographers, cardiac sonographers, is to define the etiology, the mechanism of causation, the severity, and the impact of this insufficiency on the LV chamber remodeling. And everybody knows what remodeling means, I assume. Okay, the LV is going to dilate or thicken. It's just going to change over time. So, with aortic regurgitation, as you can see, there are different pathways that come by. If it's congenital, it's probably going to be a bicuspid valve. There's different other things you can see that might happen, but typically cuspal prolapse, VSD, is associated with that sometimes, but typically a bicuspid valve is the main thing. You can also have a quadricuspid valve, a unicuspid valve, a pentacuspid valve. I've never seen a pentacuspid cuspid valve, but I have seen a 4-leaflet and a 2-leaflet valve. Excuse me, a 1-leaflet valve, the unicuspid valve. It's really kind of weird. Or maybe it's caused by some sort of subaortic membrane. If it's acquired, generally speaking, that goes 2 pathways, either valvular or the aortic roots involved, perhaps 2. Hypertension, Marfan's syndrome can cause this aortic root to increase in size, as well as the proximal ascending aorta. Valvular, it can either be acute or chronic. We're going to talk about both of these and how they affect the heart. Acute being trauma, dissection, chronic being rheumatic, sclerosis, this and that. And the pathophysiology is just as it says here. Don't worry too much about this, but if you follow this down, backward flow from the aorta into the LV, that's where it all starts. And you got an increased LV volume and pressure in the LV. Therefore, that could translate into an increased LA pressure, increased pulmonary venous pressure, and result in pulmonary edema perhaps, and so on and so forth. There's a lot of things that can go on. Increased stroke volume due to the Frank-Starling mechanism we just talked about because of the increased volume in the LV. Rapid fall of aortic pressure during diastole because it's leaking back, and so on and so forth. So, the pathophys in writing, while diastolic blood pressure is diminished and the pulse pressure widens, systolic blood pressure generally remains normal or even slightly higher due to sympathetic nervous system stimulation by the kidneys, compensating for decreased cardiac output. Interesting how the body knows this is going on. It's quite the... So catecholamines increase the heart rate, ventricular contraction strength, and cause peripheral vasoconstriction, increase in systemic vascular resistance to ensure the organs are adequately perfused. Now, that's pretty amazing that it all happens automatically. So the body knows this is going on and the heart makes the adjustments for this. It's really, I think it's pretty amazing. So let's discuss the ASE parameters for imaging and whatnot of aortic insufficiency. Our imaging views are going to be to show the doctor what's going on. We're going to show it in the peristernal long, and we're going to get a vena contracta in the peristernal long axis. You probably see techs doing this at your sites, clinical sites you're at. The peristernal short, we're going to show it there. The suprasternal view, we're going to show aortic regurgitation there, and there's going to be flow reversal seen there. In the 5-chamber view, we're going to show it there. And the 3-chamber view, we're going to show insufficiency there. This will be the peristernal view. And this here is measuring what's called the vena contracta. So as soon as the blood leaks back through the valve, the narrowest part of the jet, you can see this blood here, is aliasing like crazy through here, and the machine really can't give it a red or blue color, so it just kind of goes into the cyan color. But we can measure the vena contracta right here, and that's after it leaks in. And at the very narrowest of this point where the blood comes together, where the fluid velocity is at its maximum, That's when we measure our cross section right here. And there are ASE guidelines for the measurement of that to determine how much AI there is coming back in. And remember, we're going to do several measurements. This is only one. This gives the doctors an idea. And you can also look at the LVOT, this vena contractor. You can also compare it and see how long this here is. You can compare that to the LVOT diameter and measure from here to here, and the percentage this takes up of the LVOT diameter is another way to quantify aortic regurgitation. And so here's another vena contracta. You can see this right in this area here. It's pretty much all the way in there. The valve's pretty much getting ready to close at this point. This vena contracta will be measured right here. And in the short axis view, this is a rarity. You can see this well, but you can also quantify aortic regurgitation by how much the area is, the circumference here compared to this area here. There's a relationship between this. How much of this does it take up of this? Okay. And if you look into the suprasternal notch, we put our pulse wave up here, and we'll see, this looks like the pulmonary artery right here, and this looks like where we should be right up here. Our pulse wave will be up here. And what will happen if you red away, blue towards, so to speak, right? But what's going to happen is you're going to, red towards, blue away. So what's going to happen is you're going to get this flow coming back this way. It's going to be painted red by the machine because it's coming back towards the transducer. You can see flow reversal. And if you put your pulse wave in there, as well as your color, you'll see this here happening. This is ejection. And then during diastole, you have this flow reversal. And that's a pretty good jet of flow reversal there in the suprasternal notch. You can also see this in the abdominal aorta, or another thing we can do is in our 5-chamber view, we can show the AI, right? And we can quantify the AI by doing a PISA measurement on it. And here's our PISA formula down here. Now in the machines, either one, the ones you're using are the Epic 7s, I would hope, anyway. But there is a package in there, and we had this at Southern Maine. We don't have it at Mercy, where you can put a PISA package in there. AI, I should say, PISA package. And essentially what you do, I don't know if anybody's done the MR by PISA yet, but essentially you do the same thing. It's the same formula. The only difference being is your color baseline is going to be we're going to drag our baseline up if we go this way and use our top number for our measurement and our formula down in here, Ailerson velocity right here. We're going to use this number up here instead of this number down here as we would in MR. So anyway, we do a PISA on this, measure the full convergence zone, and we'll get a PISA shell. Measure our continuous wave Doppler of our aortic regurgitation jet, and the machine will do the formula for us. And it'll calculate out a regurgitant volume and an ERO or an EROA, effective regurgitant orifice area. And regurgitant volume would be the two things the doctors would really be looking at, these two here. And this is how the machine calculates it in the algorithm. We're going to talk a little bit about acute aortic insufficiency and the possible causes of that and what causes it. Endocarditis, a rupture of one of the cusps, dissection of the aorta, or some sort of surgeon cause during an operation or something like that. So acute AI features, you probably see normal. It's acute. It's sudden onset, so you'll probably see normal. Perhaps a slight dilatation of the left ventricle. More than likely normal, though. The heart would be tachycardic, initially hyperdynamic, because this blood is coming in there, and it's got to get it out of there. Enough out of there to keep the person alive and what have you. So short pressure half time. We'll talk about pressure half time in a little bit. Holodiastolic retrograde flow in the descending aorta. And that's what this here looks like. Flow reversal and be holodiastolic will fill up this whole diastole portion. The consequences of acute AI, basically the development of a distinct syndrome, the pathophysiological features of which differ from those of chronic. So acute AI, we have acute and chronic. We're talking about acute. Acute AI imposes a sudden excessive load on the unprepared ventricle. And that ventricle is normal in size, resulting in a dramatic increase in LV diastolic pressure, which may approach or equal the aortic diastolic pressure. So that's not a good thing. It's going to be hard moving blood around if that's the case. So because the LV pressure exceeds the LA pressure in diastole, now think about the LV pressure exceeds the LA pressure in diastole, the rapid rise in the gradient between the ventricle and the atria causes the mitral valve to close prematurely before the onset of the next pump, if you will, next systolic movement of the heart. And premature mitral valve closure is beneficial. Think about this. The heart does this beneficially. I mean, it just does this. It's actually a good thing, but it's not. So it's a good thing initially. It's beneficial in the sense that the high end diastolic pressure is not transmitted to the pulmonary venous system to cause pulmonary edema. However, which could result in clinical heart failure. However, the protection afforded by the premature mitral valve closure is essentially lost when a further rise in this gradient between the LV and the LA opens the mitral valve in late diastole, leading to what we call diastolic mitral regurgitation. Maybe some of you have seen that in your clinical sites. It's kind of interesting phenomenon. So mitral regurgitation in acute AI may occur either in diastole or systole whenever the end diastolic pressure in the LV exceeds the LA pressure. So persistence of this gradient as a result of the extension of the high end diastolic pressure extending through the isovolumic contraction period in early systole causes the mitral valve to open during this period, resulting in early systolic MR. And it's usually effective to lower. MR is helpful because it lowers the left ventricular diastolic pressure. Remember, the LA serves as a reservoir for blood regurgitated from the aorta to the LV. However, this is going to increase the LA pressure even more because there's going to be more blood up in there, leading to the potential for pulmonary edema and circulatory failure. We're going to stop there and start with chronic AI next.